Okay, welcome everybody to the fourth Compass lecture of the semester. Today our speaker is Dr. Guy Neer. He completed his undergrad and graduate studies in Israel. He finished his PhD in astronomy from the Weizmann Institute and has been a postdoc here for the last 2 years. And in his talk, he's going to talk more about himself. So let's welcome our speaker for today.
Hi, everyone. So I'm going to talk a little bit about the different steps of my career in academia so far. And I'm going to talk a little bit about the science and a little bit about the decision making. So hopefully it'll be interesting for both these things. I should say that I've had a pretty jagged trajectory through academia. So I've been jumping around from topics, from places. It wasn't really crazy, but a lot of times I didn't know really what I wanted, and what I thought I wanted, I changed my mind after a couple of years and I wanted something else, and I found out all these things in the hard way. So that's one thing. And the other thing is that I'm probably on my way out of academia and into industry now. So, you know, it's not like you can hear from your professors a lot about how to become a professor, right? But I'm going to give you the perspective of somebody who's decided that I'm probably not going to be a professor in academia. So I hope that helps you as well. But you know, if your mind is set about becoming a professor and staying in academia, then you can take a lot of my warnings, but maybe not a lot of my advices. And yeah, and I've been wrong about a lot of things, so you know, take it with a grain of salt. So for people that are not already deep into a STEM career, if you're just on your first or second year undergrad and you're wondering if this is a good idea, so here are my reasoning for going into STEM. So first of all, I always thought physics is interesting, but I also think in engineering and astronomy and biology and all these things are also super interesting. So the problem for me was figuring out what is most interesting, but I've always been drawn to physics more than anything else. And also, if you're going and you're doing grad school, you don't have to stay in academia, even though everybody tells you that academia is the most important thing, and you're writing papers and you're interviewing for jobs, and you're thinking that the only goal you have in mind is how are you going to be a professor, but that's not the only thing that can come out of being in academia. You can also find jobs outside of academia, and you get a lot of useful tools by being a grad student. So that's another reason to do it, even if you're not sure what your future is going to be like. And I think that it's important to define your life goals. I know it's kind of, it's maybe a little bit like a hippie sort of thing to think about your life goals, especially when you're 20 years old. But your life goals don't have to be like what you're going to do when you're 50 years old. It can be what you want to do for the next 2 or 3 years, right? What is it that you're actually trying to accomplish? And I think that defining that even for yourself, even if you don't tell it to anybody or write it down anywhere, just have that in mind. You can make decisions and do what is actually helping your goals and not just getting pulled by the current, which is very easy. And the other thing to consider is opportunity cost, right? Whenever you decide to take one profession, you will have to give up on a lot of others, and every choice you made has a lot of choices you don't make. And it's important to remember that when you have many options, you choose one of them, you might feel like you're giving up on all the other options, and that's actually not true. What you're giving up is one of the other options, and you're not necessarily going to be able to do all the other things just because if you took physics doesn't mean you can study biology and astronomy and engineering and all these things. If you give up physics to study something else, you'll only be able to study one of those things, maybe two. So when you're comparing the opportunity cost, you have to be honest about what you're missing and what you're not missing. All right, so I did my bachelor in Ben Gurion University in Israel. And I was really surprised to study when I studied physics in university that mechanics and electromagnetism, which is what you study in high school, that's not the only thing that physics is about. And I was happily surprised by that because, statistical mechanics I thought was super interesting, and not to mention quantum mechanics and particle physics and all that stuff, and just really opened up my mind. Towards the end of my degree, I did a little project in cosmology with like the expanding universe. I'm not going to talk too much about that, but I was sure I was going to be a theoretical physicist. So, yikes. No offense to any physicists in the audience, but yeah, that was completely off from what I'm doing right now. So it's really surprising to think that this is what I thought it was going to be. And I had the opportunity to combine physics with computer science or engineering, or do just one of them. And in terms of, making money, doing a bachelor degree in engineering, at least the programs we have in Israel, that gives you a lot more options in terms of work. Doing just a single major in physics, 3-year theoretical degree doesn't give you a lot of practical experience and doesn't help you get a job. We used to joke about this, that when you finish your bachelor degree in physics, you can go, install cable for people, cable TV, or work at the grocery. And that's the sort of jobs we thought we were going to get with just a bachelor's degree. And I think that's pretty much true. But of course, once you do higher education, you start to get more openings, even if you did just physics or just astronomy or stuff like that. But I didn't care about any of that stuff. I only cared about knowing physics. That was what I wanted to do. This was what was interesting to me. And I said, I don't care about anything else, and everything will be okay. And it's kind of irresponsible, I guess. But I also, I had the privilege that I didn't feel like I needed the money right away. I wasn't in a hurry to start making money. So I could afford to do this thing where I could just say my goal is to know physics. Obviously, if I came from a background where I had less money, I might have had slightly different goals. And I might have done something more responsible, like actually being able to get a job. But for me, this was okay. And I feel like I've done that. So knowing physics was very interesting for me, and it was goal enough on itself. Later on, I did my master's in the Weizmann Institute. I didn't get into the high energy theoretical group. They were doing like string theory and stuff like that. And I had 3 other people in my cohort, and they were all much smarter than me, and they got in. And I didn't feel too bad about that because they were really smart people. And you get to this point, especially when you start grad school, where you used to being the smartest person in your class in high school, maybe one of the smartest people in your class in your undergrad, and then you reach grad school, and for me, it was like a little bit below average in grades, at least, or in general. And then to find out there are people so much smarter than me, it was kind of sobering. So, that's something to look forward to. And to know that it's coming is kind of not to be surprised too much by this. But the fact that I didn't get into the theoretical group was really good for me, because after a while, I realized that what they're doing, like trying to solve these really, really complicated integrals and basically doing the same sort of work that we've been doing for homework and our particle physics classes, but that's what they're doing for their entire year or entire program. And that would have been a nightmare for me, I think. So it's pretty lucky that I didn't get it. I did find a niche project working on a neutrino detector that was being built at the South Pole. So that was pretty cool. And I immediately liked this because it took me a long time to figure out what I want, like which specific field of physics I want to do. And this neutrino detector thing was a lot of technical work, a lot of software. It was not like the bread and butter physics that everybody was doing, because at Weizmann they were doing like supernova science and particle physics at the LHC, and they were like, the main things that people were doing, and nobody else was doing anything with neutrinos. So I said, yes, this is exactly what I want to do. And I always thought neutrino thing was really interesting. I'll talk about that in a second. And it's the kind of project where if you find something, it's great. You publish papers, you get like a lot of publicity for what you find, but also nobody's promising you that you're going to find anything. And in fact, I didn't stay long with this. I did my master's for 2.5 years, and the detector, there was supposed to be like this modular detector that would get built over time. They didn't have enough funding. They only built a small part of it. We never found any neutrinos. We only did some simulations and published like 1 paper about that. So, okay, I didn't stay there for very long. I'll talk about that a little bit. But when I was there, I thought it was super interesting. So I learned a lot. So I'll talk a little bit about the actual science that we were doing, just because I think it's super cool. So neutrinos, if you don't know them, they're elementary particles, as far as we know. They're cousins to the electrons and the mu and tau particles. And the interesting thing about neutrinos is that they don't have electric charge, and they have very, very small mass that we don't exactly know what it is, but it's very tiny. It's much, much lighter than the electron. And they all pass through us all the time. So the entire space is full of neutrinos. They don't interact with matter almost at least interact very, very rarely through the nuclear force. And here you can see kind of the diagram where it's like a neutron turning into a proton, and it's emitting this weak interaction that turns into an electron and a neutrino. So this is the sort of interaction where you get like a proton and neutron changing the particle and and emitting, either getting hit by a neutrino and changing and turning into a different particle, or spontaneously doing it and emitting a neutrino and an electron. So these particles just pass right through us, they don't interact. And the nice thing is that there are explosions in space that produce these neutrinos. So for example, if a supernova, where a massive star collapses and then a part of it explodes out into space, during that collapse, there's a lot of neutrinos that are emitted. And one of the reasons we know this is true is that in 1987, there was a supernova on the Large Magellan Cloud, which is a small galaxy next to our galaxy. And a few hours before that supernova, we detected a bunch of neutrinos. And the reason it's a few hours before is that the explosion starts at the center of the star and starts to move outward. And the explosion itself, like the heat and the particles and all the energy that you see in regular light and in X-rays and all these optical spectrum, it takes it a while to go out of the outside of the star. So the layers of the star actually block this until the star explodes. And the neutrinos don't have that problem. They go right through the star. So some of them get reabsorbed, a lot of them just go straight through it and reach the Earth a few hours before. And that was a theoretical prediction. This is exactly what happened in 1987. And it kind of made people really, really hopeful that this is going to start a new age of neutrino astronomy. And it took a few years for people to start seeing more of these neutrinos from outside of our solar system, at least. But when you do see these neutrinos, they tell you something about the inside of the star, or the thing that explodes. Stuff that you can't see using other types of radiation and particles, because those have to go through the matter, and the neutrinos are just transparent to matter. The matter is transparent to the neutrinos. So as you can imagine, it's really hard to detect these very transparent particles. It's hard to catch them. So how do we do that? So to catch them, you actually need a big target space. So one neutrino, if you have billions of neutrinos crossing through all the time, most of them don't interact, you need a lot of mass, just a lot of target particles, so that by chance, after a year that the detector is operating, one of them will get hit by a neutrino and you'd see it. So what we do is we use either large pools of water. So you can see here an underground mine in Kamyakanda. This is a super Kamyakanda detector. And what you see are these circles are optical detectors that are very, very sensitive. And these are people on a boat. This is water here. And this is people cleaning the detectors. So it's a giant mine full of water. It's very pure water. And when one of these neutrinos hits one of the particles of the water, it emits a light flash. And you can detect that and you can say, okay, this is a neutrino. What happens when the neutrino actually hits it, if it's a very high energy neutrino, it releases one of these electrons or tau or muon particles, and these particles move close to the speed of light. And because the target mass is water, and light actually travels slower than the particle that produced it, and you get what looks like a supersonic boom. So you get a superluminal boom where you have a small charged particle moving at the speed of light, and light moving at 2/3 the speed of light, because the speed of light is different inside the medium. Right, so light slows down when you're inside a dielectric medium like water. So the light is actually slower than the particle. So you get all this light bunching up and emitted at the same time, like a supersonic boom. And then you see a flash. This is called the Cherenkov effect. So, I mean, you can see why I was attracted to this, because of the cool physics and like the rare particles and all these giant detectors. So it's kind of like, it's all really, really cool stuff. So IceCube started working. IceCube is a detector where instead of water, they built a giant cube of 1 kilometer by 1 kilometer by 1 kilometer in the South Pole ice. The ice there is very clear. And the same idea. You have photo detectors inside the ice. They just dug holes and put the detectors in. And whenever a neutrino hits that big chunk of ice, it emits one of these Cherenkov flashes, and they can see it. And actually, IceCube started detecting lots of neutrinos. So a lot of them come from our atmosphere, where cosmic ray particles, which are different types of charged particle for space, they hit the atmosphere, and some of the byproducts are neutrinos. So those we have many of those. We have some neutrinos coming from our own sun. They're slightly lower energy from nuclear interactions in the sun. But what you're really looking for is the neutrinos with higher and higher energy that come from outer space. And one of the ways to actually do that is in IceCube, one of the ways they do it is they look for neutrinos that come through the Earth. So these are actually more rare, and because neutrinos can pass through the entire Earth without getting blocked most of the time, so you can actually see more neutrinos when you're looking down. So you'll be looking north from the South Pole at the sky. So that's the IceCube neutrino, and it's been working, and it's actually detected many neutrinos from space, and they're starting to close in on where these neutrinos come from, which is still an open question, and it's really interesting stuff. So I thought this was really fun thing to join, and the thing that I was working on is called the Ascarian radio array, where if the neutrino is even more energetic, then instead of, so on top of generating just visible light with the Cherenkov flash, it can also generate radio waves. So the idea here is that you can see these radio waves much further away than you can see an optical flash in visible light. And the idea was to build a detector that spread out over 100 square kilometers instead of 1. So much bigger target mass to look for these much rarer high energy particles. And they built 5 stations out of the planned 37. You can kind of see the map of the planned stations. 5 of them were operating when I was there, but there was never any money to build more of them, and some of them stopped working, and then they had to fix them, and it was a big mess. And this experiment, as far as I know, still hasn't produced any results, even though it's like 10 years after. So my master's advisor told me, look, it's not getting built. It's going to be really bad for you if you spend another 5 years as a PhD student working on this and not have any actual results. So she told me I should probably change subject, and I took her up on her offer. And yes, and unfortunately, I did not get to go to the South Pole to work on this detector. I was too junior to do any of that stuff, although I really wanted to. But yeah, I thought it was really cool, and that was my master's project. Anybody have any questions on this before I pivot to something else? No. All right. All right. I continued in Weizmann. I just changed an advisor for my PhD. This time I was doing something a little less exotic with an optical telescope, so visible light, just a small 0.5 meter telescope, not something crazy. He told me we're going to get the optics in the summer, and then we'll build the telescope. And I was naive, and I didn't ask him summer of which year. So eventually it took like 3 or 4 years until we actually got the optics, because it turns out that when you make custom optics, you send them to be produced somewhere, and they sometimes run into problems, and their device can't do the thing that you want with the lens and the mirror and whatever, and then it gets delayed sometimes by many years. So this is the sort of thing you have to be careful if you're going into an experiment and it's about to start construction, right? So you have to be very specific, like, is this experiment actually going to be built while I'm still in grad school, or is it 2 or 3 grad lengths away from being built, in which case you don't want to be in it. So this is the sort of thing I learned the hard way. But yeah, the idea was that we're going to build the observatory, everything we're going to buy and construct, and all the code that will interact between the different parts of the observatory, like the dome opening, closing, the weather station that automatically closes it if it's raining, and the telescope supposed to slew to the right target, and everything we were supposed to do by ourselves. When I say we, I actually mean me. And the thing that was special about this is that we're looking for very rare events, which I'm going to talk about in a second. And we're using this camera that takes 25 images every second. So in astronomy, generally, what you do is you point your camera and you observe for 30 seconds or 30 minutes and stuff like that. So for us to observe at 25 frames in each second was very unusual. So this is very high frame photometry. And there are very few telescopes in the world that are actually still doing this kind of thing. And also it was kind of a high risk, high reward project, just because you don't know how many of these things you're going to find, if they're exotic and they're rare. And you're using equipment that not a lot of people are using. So, immediately I was attracted to this project, of course. But yeah, so it's kind of the same story, just in astronomy now. So let's talk about the science. KBO occultation. So Kuiper belt objects, or KBOs for short. So the Kuiper belt is this band of icy, rocky bodies that are outside the orbit of Neptune. And the reason that it's outside the orbit of Neptune is that everything inside the orbit of the planets, basically, Neptune is the outermost planet, of course, everything inside there, where the planets formed, all these little rocks got thrown out, except for the asteroid belt, which is a small, relatively small number of asteroids in there. So in the Kuiper belt, there's a lot more asteroids that are left. I don't know if to call them asteroids or comets. It's not exactly clear what the distinction is at that point. But it's a reservoir with a lot of these icy bodies. So we know about them because the big ones you can see with direct imaging with telescopes, with big telescopes, down to about 45-kilometer radius. But the smaller ones, I'm talking about kilometer-sized rocks, basically, you can't see them. They're too far away from the sun. They're very, very faint. You can't see them with any telescope that we have. So one way to see them is if they accidentally hide their light from a star for a fraction of a second. So we call this an occultation. And you don't know where they are, so you're basically blindly searching for them. And you're waiting for just a chance coincidence that this tiny rock is going to occult this tiny star, this tiny point in the sky. And you can already kind of get a feeling for the fact that this is pretty rare. So based on the information that we do have, the thumb rule is that each star gets occulted once every 10,000 hours. So that's a really long time to wait while staring on a single star, of course. But if you observe many, many stars in the same field for a long time, then you might get a few of these. The occultations themselves are really quick because the object is moving and the Earth is moving, and the object itself is a kilometer-sized object, and the Earth itself is moving at 30 kilometers per second. So you can do a very simple calculation. You get to that it's less than a tenth of a second by the time it crosses. So it's really, really fast, much, much faster than any other thing that you see in astronomy, basically. And it's very, very rare. So there are a couple of detections from Hubble. They're guiding cameras taking images at 40 frames per second. And by chance, after 10 years or 20 years of observations, they saw a couple of these instances of occultations. And there's one detection from the ground that I actually show here. This is basically the light, because this is the amount of light from the star. And you see that for a tenth of a second, it dims out, and you can see on the scales, it goes from 0.1 to 0.1. This is all you get. And the event never repeats, and you have to figure out what it is. So very exotic, very hard to find, very technically challenging, lots and lots of data that's being produced by the camera, all the stuff that I like to do. So of course I went for this project immediately, and I said yes. Yeah, that was maybe not the best idea, but I had a lot of fun doing it. So we built this telescope. It's actually moved from the location that you see here now, but this is the way it looks. This is the dome that we built. This is a telescope. You can kind of see it's red because of the red filter. It's custom optics, like I said, took a lot of time to get them. Very fast camera. We basically got this lot inside of another observatory's fence, but that's it. We built everything else by ourselves. Let's see. Took me several months to actually write the code to make the telescope operate robotically during the night, which took me not a lot of time because I wasn't sleeping at night until the telescope started to work on its own. So that I had a very high incentive to get that piece of code working. And yeah, so I started my PhD in 2014, and after all these delays, we actually started taking useful data in 2020. So you can already see your advisor tells you, I have this project that I'm thinking about building, and you want to be part of it. And you say, no, I want to be part of the project that you have already built, or that it's the last stages of construction, at least. Or at least you need side projects, right? Yeah, so I think I talked about most of this stuff. So this is the sort of thing that we were doing, and I really liked it. I enjoyed it a lot. Here are some pictures from where we're constructing. This was my advisor. You can see we were doing a lot of the very intelligent and important knowledge work when we were doing this thing. This is me putting stickers on the cables, building the parts of the dome. This is the actual telescope. Yeah, this is fun, I have to admit. I really enjoy this. All right, so what's the conclusions from all of this? I'm going to tell you my conclusions, even though we haven't published them, but we're publishing them probably next week, so I think it's okay. Yeah, so we didn't find any occultations. I think that I made that clear, sort of hinted at this. After 2 years of data, we didn't find anything. And in fact, the limits we put on it, if you can see the line, this is the thick line is our limits, and this dashed line is the limits from one of the previous surveys that used three telescopes over 7 years, and they got about the same results as we did. So that's encouraging, but also kind of depressing at the same time, and depends on how you look at it. Yeah, and we probably ruled out the one detection from the ground survey, and they worked for like a couple of months and they already detected something, and we were observing with a bigger instrument for 2 years and we didn't find anything. So it's probably ruled out. So it seems to me that actually the detections that people think they have are not real, and that these small objects are more rare than people think, and it's actually much harder to do. So that's an important conclusion, but it's also kind of depressing because it's a null detection. And when you're doing science, you always have the possibility of getting a null detection. But that's less exciting, and it's less gets you into a Nature paper, unfortunately. So, all right, so I will summarize this part of my talk, and I don't have much more. Was it a good idea, right, to go to grad school after all of this? So, first of all, any questions about the actual science, about the KBOs, about the occultations? Make sure, no? All right, so I did learn a lot in terms of astronomy. Even outside of my own project, I was sitting in the group meetings with my friends that were all doing other things like supernova science, and I learned a lot just by listening to them talk and discuss papers. So, you're immersed in this for a few years. Of course, you learn things, even if they're not exactly inside your own field. And in my own field, I feel like I did learn a lot about these Kuiper belts and the Oort cloud, which is even further away, and planet formation, all these things that you learn while you're writing the papers and when you're working on this stuff. Unfortunately, because I had all these technical problems I had to solve, I wasn't doing a lot of science. So I wasn't reading so many papers. I wasn't writing a lot of papers, and the ones that I was writing weren't really science heavy. And I felt like this was kind of a missed opportunity, because I was enjoying this technical work and I was doing all the technical work, but I didn't get to discover things, and publish things. And this is kind of what they expect from you in academia. So I felt like I was missing something. And my advisor said, "You're enjoying the technical stuff too much." And I went to a postdoc. He said, "You have to be careful not to invest all your time in the technical stuff, because that's what you like, and you need to do the other thing." But on the other hand, I did have to contend with a lot of what I call non-textbook questions. And this is one of the big differences between doing undergrad studies and the grad school. You go to grad school, they no longer give you questions that if you can turn the book to the end and you can find the answers, right? You're facing questions that they don't have answers. You don't know how many KBOs are out there. You don't know how to solve your problem with your telescope that's not moving correctly. It's on you. So my wife told me several times, when she saw me sitting like this and trying to figure out something in my code that doesn't work, she said, "Can't you ask somebody to help you?" I'm like, "No, I mean, I'm writing the code for this camera that runs super high rate, and there's nobody else that's doing this. It's the stupid code that I wrote that's malfunctioning. There's nobody else in the world that can help me now." So it feels kind of lonely sometimes. If you're lucky, you're working on a project with at least other students, and you can kind of bounce ideas off them. But even then, a lot of times you're on your own, even in a small group on your own. But that gives you something, right? So a lot after that, when you get a job somewhere, even if it's not in academia, people, I hope at least, will appreciate the fact that you can cope with these questions that are open, that don't have an answer. All right, so one of the things we were talking about when we were doing grad school, especially when we finished masters, and some of our friends left for industry jobs and we stayed in to do a PhD. One of the questions we thought is, what's the difference? What's the opportunity cost, right? If I go to industry now, instead of doing a PhD, just with my master's, where I can already get a job either in programming or other kinds of high-tech industries, I can get a lot from doing that, right? You have to compare not just your starting salary, but if you wait for 5 or 6 years to finish your PhD, how much work experience your hypothetical self is going to get in the industry, and how can you compare? So getting a PhD might open up better jobs for you, because they appreciate all the work you've done, and they see all this, and you have much more experience than just the 2 years in masters. But on the other hand, the opportunity cost is how much work experience you're missing, and that counts for a lot in the industry, of course. So this is one of the considerations. But like I said, I didn't really know what I wanted, so I'll do grad school. I'll figure it out. I'll see if it's for me or not. Yeah, so I'm now publishing these last results. So it took me a really long time. Everything got delayed. Everything got much slower than I thought. But yeah, so I did have some side projects, which is super important. I wrote a couple of papers on algorithms. We did find some satellite glints with WFAST, with the telescope that I built. So we did publish some stuff, and I did work on some side projects that gave me a lot. But again, for me specifically, all these things were not really sciencey, right? Writing an algorithm paper about how to find streaks in astronomical images, that's nice, but it's not the thing that gives you grants and gives you the best jobs in academia. But it is important to have side projects, especially if you're counting on building this big thing. You think it's going to produce all this wonderful science, and you don't know what kind of delays you're going to have. So you always have to make sure you have smaller projects, hopefully about science and not just about technical stuff. So that in case your big project doesn't pan through or just get null results, you still have something to show for it. So this is super important. I'm glad that my advisor and the head of my group, they were always telling me, like, you should also work on other things while you're doing all this preparation for the telescope to be built, and or when you're waiting to collect data. Yeah, so again, the upside for being in academia, you can learn a lot of things that are very hard to learn if you're just, putting your head down and doing what your boss tells you in an industry. In academia, you learn a lot of these skills that I think when you're looking for a job could be useful, even if you're leaving academia. So non-textbook questions, we talked about that. Critical thinking. I don't know how it is here in Berkeley, but at the Weizmann Institute, especially, people would get killed on seminars. Like, they would be very, very critical about what people are saying. If you can't back up what you're saying, and when you read papers on journal clubs, will always be very critical of them. So you learn a lot of critical thinking and how to actually get some piece of information and think deeply about it and criticize it and find the holes in it. So I think that's a really important skill. Communications, right? If you're doing presentations, if you're writing scientific papers, if you're talking to a group, it's much more than just sitting down writing code, right? You have to interact with other people. Data analysis and statistics, of course. If you're working in a group in general, if you're collaborating with not just your advisor, with other students, if you're mentoring, if you're working with more junior students than you, that all that stuff counts. And in my case, at least, I did a lot of software engineering, but that was very specific. But I think in most of the STEM fields that you'll see, there's always going to be some level of writing code. So it is a useful skill that you get. So that's my my pitch for you for why you should go to grad school. All right, so coming up to I think the last part is for me deciding on a postdoc, right? So I finished my, I graduated, and then I was thinking, what do I actually want to do? So I had to decide what I want to do when I grow up. It's about time that I do that. So because I didn't get to do a lot of science in grad school, I thought that I need to give it another chance, move to a different place, work on different projects. I wouldn't have this very heavy technical thing to build. I would just, do my science. So I set up a new life goal because I felt like I knew physics, I knew astronomy, I already have all the tools, but what do I actually want? And I said, okay, I'm going to devote the next 2 years to figuring out if I fit into academia or not. And this was one of the goals I had in coming here. I did a pivot to a different topic, which is super hard at this point, because when you're making proposals for a postdoc position, you're not just coming to your advisor and saying, tell me what to research, right? You have to decide what you're going to research and propose that. And it has to be something that you're good at, something that's doable, not completely fanciful, and something that is actually interesting to other people. And the intersection of these three things is actually a very hard target to hit, especially if you're moving to a different field, because you can't just make shit up. The people that are reading your proposals, if you say, I'm going to start working on black holes, right? The people that you're proposing to know a thing or two about black holes. You can't just make stuff up that will never happen. You have to do something that's actually doable. But then you can't choose something that's too easy, because that's already been done to death, and it's not going to be an interesting paper when you publish it. So you need to propose something that's hard to do, but still doable, but it's within, and it also has to be within your abilities. So you have to say, I'm the one who's going to do it best, right? Maybe other people have already thought about doing this, but I'm the best person to do that job. So this is a difficult thing to do. And I spent the last few months of my PhD reading so many papers and so many things that it was crazy, and trying to put together some proposal. And a lot of places that I sent my postdoc proposal to got rejected from. And that's not unusual. Usually you send to 100 places, and each one of these places has 1,000 candidates. So you shouldn't be surprised that you don't get into most of them. That's just statistics. But all the places where you need to do sciencey things, I wasn't getting into, because I didn't have any scientific papers and I didn't have any background showing that I can actually do that. So this was pretty hard for me, because I was in this niche of doing technical work. I did get offers to do that. So once you get into this position of of doing only the niche technical stuff, then there are fewer jobs that want you. But the ones that want you, they're going to need you much more than you need them. So because there's not so many people in academia that are really technically oriented. I got offered in Hawaii to work on a survey that they were looking for asteroids. So I had a bunch of things that are related to that, like my algorithm papers. And I told them no for various reasons. And then I tried again. I wanted to get something like a big name university. I got offered in Tucson to work on the next generation big survey at the LSST, if you've heard about it. I was supposed to do commissioning for them. Then it was COVID and everything got canceled and that job kind of disappeared, which was lucky because I don't know how I would have been flying over to Chile for a few months. I'm not sure my wife would have liked that too much. But yeah, so anyway, after that job basically disappeared, I saw a posting for a job in Berkeley where the main part of the job was writing the software suite for astronomy, which is called Sky Portal. And I said, oh, no, that sounds exactly like what I do, right? It's software, it's very technical, it's great. So I got accepted to that, which is great because here in Berkeley, you have an excellent astronomy department. And I go to seminars on all the different topics and it's just amazing. It's much more diverse than what I had in Israel, for sure. And I get to work with people on different projects and different, it's really, so it's a really good place to be doing science. And I talked to my advisor and I told him I'm going to do 50% of the time on the technical stuff from writing this code for the software project, and the 50% of the time working on my own project so I can have a chance to do the science. That's what I'm here for. And in my proposal, I had a bunch of things, and none of them I actually turned into real projects, which is kind of common for postdoc proposals. You propose something, and they say, okay, that sounds reasonable. You come there and you change your mind, you do something completely different. And I hear from a lot of people, this is the way it goes. But okay, I found something to do with the self-lensing binaries. So I'm going to talk about that a little bit. But this is the thing that I was working on for the last year and a half. All right, so gravitational lensing, right? Completely different topic. Again, like I said, I pivoted to something else. So if you have a massive object that has a lot of gravity, the light actually bends around that object. So this is cool in itself. You can already feel like the cool physics. This, of course, is going to be attractive for me. So, so if you have our sun or large galaxy clusters or black holes, they will bend the light around them. If you have, for example, in this image in the corner, you have a galaxy, and behind it, there's another galaxy, and it gets squished up and twisted into this ring because of the gravitational lens. It's kind of light moving from all different directions around this gravitational mass. And it makes things brighter, not just distorts them. So strong lensing is when you have these galaxies that change shapes and get bigger. And for micro lensing, it's when a star in our galaxy has just a point of light. You don't see the star itself, you just see a point. It's not resolved. And then there's another massive object, either another star or a black hole or a planet or something, moves in front of it and increases the amount of light. And you can kind of see here, this is the simulation tool that I've written. You can kind of see what happens when you have a lens in the middle and the light goes all the way around, and then the lens moves a little bit. So the shape of the star kind of gets twisted. At some point, it becomes two sources. But this thing is much too small to see in your telescopes. You don't actually resolve it. So that's what we call micro lensing, because it's too small to actually resolve. But you can see it getting brighter. So here you can see the amount of light coming off from the star, and it's getting lensed, so it's getting brighter and brighter and brighter, and then decaying again. And you can see this thing takes about 20 days, right? So this is already much slower than the sort of thing I used to do with like a sub-second fence. Okay, nice. This is a nice thing. So lots of people in this department, in the astronomy department, are working on micro lensing, and there are surveys looking for them, and it's all a really, really interesting field of study. But I didn't want to do like bread and butter micro lensing. That's boring. I wanted to do the exotic stuff, of course. So what are self-lensing binaries? This happens when you have two objects orbiting each other in a binary, and then they will lens each other. So for main sequence stars, because they're close together, the lensing effect is too weak. And for regular stars, you just don't see anything unless you have a super high precision instrument like Kepler Space Telescope. And in fact, they did find 5 of these objects where a regular star, what we call main sequence star, had a white dwarf, which is a much smaller but still massive object moving around it, and they could see the lensing from these 5 systems. But that only works in the Kepler data, and they already found, I think, all the systems that they have there. It's only a small footprint on the sky. So I wanted to look on the entire sky using surveys that don't have such high precision. So I wanted to look for smaller objects where the lensing would be more pronounced. So I'm looking for white dwarfs that have in orbit around them either another white dwarf or a neutron star or a black hole. And all these types of stars are basically regular stars that finish their fuel, their nuclear fuel, and collapsed into something much, much smaller. So a white dwarf is the mass of a sun, but is the size of planet Earth, roughly. A neutron star is much, much smaller than that. It's just a few kilometers. And a black hole is a little bit smaller and is even more exotic because, as you know, the light can't escape and all that stuff. But for me, it doesn't really matter if it's a black hole or a neutron star. What matters is that it's very small and very massive. So it has the potential to be an effective lens, even when it's close to one of these white dwarfs. So the self-lensing flares are different from the regular microlensing flares that happen over days or weeks, because the binary is orbiting around each other, not just random stars in the galaxy. So they're much quicker and they're often a lot more faint. But the fun part is that they're repeating. So if you see one, you think maybe this is a self-lensing flare, you can observe the same object for a while and then you see it again. If you see the same thing again repeating with a period, then at least you know what it is. So this is much better than the regular microlensing events where it happens and then you never see it again, or the KBO occultations that we had such a hard time figuring out if it's real or not real, just because it's a one-off event and you can never go back and follow it up and see if it's real or not. So in this case, you can easily follow it up. So this is a nice perk. And you can learn a lot about these systems. So if you know that it's a self-lensing system, you can measure the masses very easily. You can measure the sizes of the star. You can know everything about the system. So you get a ton of information. And this is interesting because the very question of how these white dwarfs reach the situation where they're so close together, they must have at some point been inside the envelope of one another. So, and this is something we don't know about. It's called the common envelope phase. So the common envelope evolution of stars and binaries is something that we actually don't know a lot about. And people are doing models and simulations, but nobody knows if it's true or not. So if you find a few of these systems, you can verify if the models are correct and choose the right models. So this is a really interesting science case. And here you can see an example again from one of my simulations where you see the light from the star going up and down. And here you see that instead of 20 days, you have a few hundred seconds. Okay. And you can also see, so I think I have here, the event time is, 1,000 seconds. And the period is 22 days. So you see, this is a pretty rare thing. You have to be right on time for those 1,000 seconds inside of a period of 22 days. So it's a rare event, but it's repeating. So the duty cycle is 1 over almost 1,700. Okay, so can we actually detect these things? So I went and did all these simulations and calculated exactly what the surveys would see and how much time they're observing and what each of these systems would look like with the simulator. I wrote this big simulator code that's super fast. And as you can see, I was really enjoying the technical part of all this project. But then I saw that it's actually pretty hard because the systems have to be really edge on and you have to view them right at the right time. And most of the surveys that we have don't observe the same part of the sky many, many times. They do spots on the sky, and then the chance that you will actually see one of the systems is very, very low. So I calculated what would be this is the expected number of double white dwarfs in the galaxy. And with the surveys we have now, it's way too low. Maybe with surveys that we will build, the LSST, maybe we'll be able to see some of these things, but right now, probably not. But after doing all these simulations, I can tell you what the parameter space looks like. So I'm not going to go into this too much because I'm running out of time, but basically it tells you what kind of orbits you can expect to see these double white dwarfs or the white dwarfs of the black holes. And it gives you a much better map of where you can expect to see any of these things. I don't want to go in too much detail. I will say that after doing all this research and figuring out all the parameters and understanding what happens, I realized that there are similar objects which are eclipsing white dwarfs. So double white dwarfs that are orbiting each other. If they're close to each other, the lensing effect is too weak. And what you see is basically an eclipse. They just hide each other. So we have a few of these systems, like 10 systems, or I don't remember how many, but not a lot of them. And the periods are pretty short, it's between 7 minutes and 1 hour. And then for the self-lensing flares, they have to be further apart and moving slower also. So the lensing would be stronger than the eclipse. And what happens is actually the probability to see a flare just because of geometry goes down the further away the two objects are from each other. So if you have 10 of these eclipsing white dwarfs, if you look for wider orbits, you're going to have much, much fewer of these events. So even with this back of the envelope calculation, even before I started this project, I could have told you with the surveys we have, it's not going to be possible to do it. But of course, that's the sort of thing the conclusion you get to when you're, after you do all the simulations and you're smarter and you understand how the different parameters affect what you're doing. So, I could have saved myself a lot of work, but I don't think I was smart enough to do that before I started this project. Okay, so this is what I was telling you about. Yeah, so like I said, we're going to get a roadmap at least. So this is the paper that we're going to write. It's going to be another null detection. There's Curious, which is a fleet of CubeSats that is being built here in Berkeley that I'm collaborating with people that are building it. So if at some point they build this fleet of satellites, they're probably going to be able to find these self-lensing flares. Of course, I'm not counting on that to publish my paper because that's a few years in the future. So it's a nice thing to be able to say, well, in the future, they'll be able to find it. But yeah, like I said, you can understand why I like this project. And you can kind of see a repeat pattern here, right? I'm landing on these projects that are very technical, very hard to do, kind of a long shot projects, niche physics. And then I can complain that if I didn't have null detections, I would have all these wonderful papers that I can go and get an academia job with them, right? But it's also kind of tells you something about the choices of projects that I've made, because if I was choosing projects that are less niche and less high risk, high reward, just doing a regular paper about a supernova that exploded, sort of boring stuff that scientists do, then I would have scientific papers that I could publish and I can at least show that I know how to do the bread and butter stuff. I was always attracted to this stuff. So if you really want to be in academia, you have to hedge your bets a little bit and not just go heads first into the hardest projects you can find. But on the other hand, I did have a lot of fun and I did learn a lot from these projects. So maybe not really scientific stuff, but still important. Right, I will be I'll be moving up to the Berkeley lab next week, actually, to work on writing software for a new sky survey. I sort of achieved my goal of understanding if I want to stay in academia or not. I figured out after a year and a half, it's not happening. I'm not writing all these science papers. I'm not doing all the science. I'm doing all the software and I'm enjoying it more. This is what I like. I highly recommend it, but everybody has to choose for themselves what is the thing that they actually enjoy to do. You have to be honest. I mean, if this is what I like, and this is what I should be doing, and I can complain that if they weren't null detections, I would have 2 Nature papers about the KBOs and the self-lensing flares, but they're not. They're null detections, so we're going to publish them on less fancy journals. But it's not just bad luck, right? It's the decisions that I've been making. And I don't have to stay in academia. I can find a lot of technical things to do that are very interesting and they don't have to do with astronomy, even though being an astronomer is cool. And I like to say to people that I'm an astronomer. So, just to say to people, I'm a professor of physics or I'm a professor of astronomy is like, it sounds so fancy, but for me personally, I don't think that's good enough reason to make all my life decisions based only on that. It is part of it, but it's not only that. And I think knowing astronomy is good enough for me at this point in my life. And I kind of want to leave you with this. I thought about this when we were writing the KBO papers, and I thought, we're putting these limits, and our telescopes can't really find all these things. And maybe if we observe for another 10 years, we'll know how many KBOs are out there. And I was thinking, I could go back to Weizmann Institute and do like a research associate or something and work on this for another 5 or 10 years. And I would know the answer. How many KBOs are out there? I would know. I would be the one finding them. But on the other hand, I could also, if they offered me the answer to this question in 5 years from now, or I don't know, $1 million, what do I prefer, right? And so I assume that for some people, knowing the answer is like much more important than the money. And if you ask me when I was 23 years old, that's probably what I would have told you easily. I don't care about the money. I only care about the science. And today I'm thinking, well, that money sounds nice. Somebody else can figure out the answers. It don't have to be me. I don't have to be exactly the person to find, to invest the next 10 years of my life to find the answers. So this is the sort of opportunity cost that you're thinking about it. At some point you're saying, well, I can invest another few years they can also put those years to do something else, which could be equally interesting and, might even help people, not just, in millions of light years from us, figure out things that are here. Yeah, so let me see if I skipped anything. So STEM graduate education is really good, even if you're going to industry, not just for academia. It is okay to study something just because you're curious about it. And you can decide that you just want to learn biology or whatever, astronomy. I think it's really important to focus on the things you're learning, not just on the actual achievements that you can put on your resume. Like, I wrote this paper and now you can accept me to your job. Right? The tools that you learn, like if you wrote this amazing code, the 30,000 lines of code that do these cool things for a specific experiment, you can't use that. But what you learn from writing that code, you can use. You can usually also copy paste parts of it to your new project. That's a different thing. Yeah, so a successful career, so turning into a professor, does require some luck. So you can always fall on these projects where you don't get anything and it's not fancy and you don't get fancy results. But if you hedge your bets and you have some strategy about this, you're not going to be completely dependent on just that one paper that you publish when you find the results. You have to have a strategy that doesn't make you completely dependent on luck. And I think that considering the opportunity cost at every point of the way and considering what it is that you actually want to achieve in the next few years, it's important. And then when you finish, when you look back at your decision, you can say, well, I didn't get where I thought I was going to get. But when I made that decision, it was the right decision because I was fulfilling the life goals that I set for myself at that point. And that justifies, at least for me, that justifies some of these decisions where, you're making decisions when you don't know what the future holds. But you can say, well, given the information that I have, I made the best decision possible. And you don't regret it if you actually work this way. But I think that defining to yourself what it is you actually want to achieve is really important, because otherwise you're making decisions basically on, on a whim or thinking that you know where you're going to get, and nobody knows that. So yeah, thank you. Any questions?
A little short on time, but if you
Okay.
have any questions for our speaker, feel free to talk to that. So let's thank our speaker one more time.